हेलो बच्चों, ਅੱਜ ਦੀ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਸਾਡੀ ਅੱਜ ਦੀ ਡਿਸਕਸ਼ਨ ਦਾ ਟੌਪਿਕ ਵੈਂਡਰ ਵਾਲਸ ਇਕੁਏਸ਼ਨ ਹੈ। ਪਰ ਟੌਪਿਕ ਸ਼ੁਰੂ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਅੱਜ ਦੇ ਟੌਪਿਕ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਜਾਣਾਂਗੇ ਜੋ ਕਿ ਇਸ ਤਰ੍ਹਾਂ ਹਨ।
Upon completion of this topic, learners will be able to discuss assumptions of kinetic theory of gases, discuss behavior of real gases and deviations from ideal behavior, differentiate between ideal gases and real gases, discuss van der Waals equation.
Kinetic molecular theory of gases. Students, various gas laws which we have studied so far are based upon experimental facts. In order to explain the behavior of gases, Maxwell, Boltzmann, Clausius, etc. suggested theoretical model of the gas which is known as kinetic molecular theory of gases. Students, आओ हुन postulates of kinetic molecular theory of gases बारे गल करते हैं। Kinetic molecular theory of gases, they postulates the main points इस तरह हैं। Every gas is made up of a large number of extremely small particles called molecules. The actual volume occupied by the molecules is negligible as compared to the total volume of the gas. The distances of separation between the molecules are so large that the forces of attraction or repulsion between molecules are negligible. Particles of a gas are always in constant and random motion. If the particles of a gas were at rest and occupied fixed positions, then a gas would have had a fixed shape which is not observed. The molecules are supposed to be moving continuously in different directions with different velocities. Hence, they keep on colliding not only with one another but also on the walls of the containing vessels. Collision taking place between these molecules are called as molecular collisions. The pressure exerted on the walls of the containing vessel is due to the bombardment of the molecules on the walls of the containing vessels. Collisions among gas particles are completely elastic in nature. It means that total energy of molecules before and after the collision remains the same. Different particles in the gas have different speeds and hence different kinetic energies at any specific temperature. Average kinetic energy of the gas molecules is directly proportional to the absolute temperature. Students, now we will discuss about ideal and real gases and behavior of real gases at different pressure and temperature conditions one by one. First, let us try to recall definitions of ideal and real gases. A gas that obeys gas laws and ideal gas equation under all conditions of temperatures and pressures is known as ideal gas. Such types of gases are imaginary. None of the actually known gases such as oxygen, nitrogen, carbon dioxide, etc. obey the ideal gas equation over the entire range of temperatures and pressures. The gas which does not obey ideal gas equation and gas laws at all temperatures and pressures is called non-ideal gas or real gas. Amagat Andrews and other scientists made extensive study of the behavior of various gases under different conditions of temperatures and pressures. They concluded that real gases do not obey the ideal gas equation under all conditions of temperature and pressure. Students, with the help of shown graphs, we will try to understand the deviation in gases from ideal behavior.
To understand the deviations from ideal behavior with respect to pressure, let us study PV versus P plot for dihydrogen, helium, carbon monoxide and methane gases at constant temperature. Along x-axis, pressure P and along y-axis, PV have been taken in the graph. According to Boyle's law, PV will be constant at constant temperature. Hence, PV versus P plot will be a straight line parallel to x-axis at all pressures and at constant temperature. Students, look at the graph at 273 Kelvin temperature. PV versus P plot for real gases like carbon monoxide, methane, hydrogen and helium is not a straight line. Two types of curves are observed. In the curve for dihydrogen and helium, as the pressure P increases, the value of PV also increases. In the case of other gases like carbon monoxide and methane, first there is a negative deviation from the ideal behavior, that is, first PV value decreases with increase in pressure. It reaches to a minimum value. It is characteristic value of a gas. After that, PV value starts increasing with the increase of pressure. The curve then crosses the line shown for ideal gas and after that shows positive deviation continuously. Real gases show ideal gas behavior at a very low pressure 1 to 10 bar. Deviations from ideal behavior also become more clear from pressure versus volume plot of experimental data and that theoretically calculated from Boyle's law. Let's study one such plot. Let's take volume along x-axis and pressure along y-axis. The curve or isotherm for real gas should coincide with the curve for an ideal gas. However, the two curves are not the same. At high pressures, the measured volume is more than the calculated volume. But at low pressure, experimental and calculated values of volume come close to each other. From this pressure versus volume plot, it is quite clear that gases show ideal behavior at very low pressure.
Students, the extent of the deviations of real gases from ideal gas behavior at different pressures can be measured in terms of factor known as compressibility factor Z. This compressibility factor Z is equal to PV upon nRT. In this equation, P denotes to pressure, V denotes to volume, T denotes to temperature, R is the gas constant, N is the number of moles. Let us study variations of compressibility factor Z for nitrogen, hydrogen, oxygen, methane and carbon dioxide gases at different pressures at constant temperature.
Let's plot one more graph for nitrogen, hydrogen, oxygen, methane and carbon dioxide gases between pressure in bar versus value of Z, that is compressibility factor at 0 degree Celsius. Along x-axis, pressures in bar and along y-axis, Z compressibility factor is taken in the graph. For an ideal gas, PV is equal to nRT. That is, PV is equal to the number of moles small n multiplied by R multiplied by T for all temperatures and pressures. Therefore, Z is equal to 1. The graph of Z versus P will be straight line parallel to pressure axis at a given temperature for an ideal gas. Students, for gases which deviate from ideality, value of Z deviates from unity. For hydrogen gas, value of Z compressibility factor is greater than 1 as shown in the animated graph. Z is greater than 1. Here, PV is greater than nRT. This means that these gases are less compressible than expected from ideal behavior at all pressures. For nitrogen, oxygen, methane and carbon dioxide, value of Z compressibility factor is less than 1 at low pressure and greater than 1 at higher pressure. This means that these gases are more compressible at low pressure and less compressible at high pressure than expected from ideal behavior. So, it is very clear from this graph that at very low pressure, all gases have Z is equal to 1 and behave as ideal gas. At high pressure, all the gases have Z is greater than 1. It is very difficult to compress them. At intermediate pressures, most of the gases have Z is lesser than 1.
Students, now we will study the effect of temperature on the behavior of gases. This can be understood by comparing behavior of nitrogen gas at different temperatures.
ਆਓ ਹੁਣ ਅਸੀਂ ਨਾਈਟ੍ਰੋਜਨ ਲਈ ਕੰਪਰੈਸਿਬਿਲਿਟੀ ਫੈਕਟਰ Z versus pressure P ਦਾ 223 Kelvin, 273 Kelvin, 323 Kelvin, 373 Kelvin temperatures points ਤੇ ਇੱਕ graph plot ਕਰਦੇ ਹਾਂ. Nitrogen gas shows maximum deviation at 223 Kelvin temperature. As dip in the curve is maximum, the dip in the shown curve decreases as the temperature increases. At 323 Kelvin, the dip in the curve almost disappears and the curve remains horizontal for a large range of pressures, or at this temperature, nitrogen nearly becomes ideal and obeys Boyle's law. ਇਸ ਟੈਂਪਰੇਚਰ ਨੂੰ ਬੋਇਲਸ ਟੈਂਪਰੇਚਰ ਜਾਂ ਬੋਇਲਸ ਪੁਆਇੰਟ ਕਿਹਾ ਜਾਂਦਾ ਹੈ. ਇਸ ਲਈ ਬੋਇਲਸ ਟੈਂਪਰੇਚਰ ਨੂੰ ਇਸ ਤਰ੍ਹਾਂ ਵੀ ਡਿਫਾਈਨ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ ਕਿ the temperature at which real gas behaves like an ideal gas for appreciable range of pressure is called Boyle's temperature. From the study of all these four graphs, it is very clear that real gases at low pressures and fairly high temperatures ਉੱਤੇ ideal behavior show ਕਰਦੀਆਂ ਹਨ। Low temperatures ਅਤੇ high pressures ਤੇ gases ideal behavior ਤੋਂ deviate ਹੋ ਜਾਂਦੀਆਂ ਹਨ।
Students, now we will try to understand the causes of deviations from ideal behavior. Van der Waals explained that two faulty assumptions of kinetic molecular theory, these are causes of deviations. Now we will discuss these two faulty assumptions of kinetic molecular theory and how these are responsible for deviations in behavior of gases from ideal behavior. First assumption is the volume occupied by the gas molecules is negligible as compared to the total volume of the gas. So, the volume of the gas is the volume of gas molecules and also of the empty spaces among them. Moreover, the molecules are incompressible and it is only the volume of the empty spaces which increases or decreases during expansion or contraction respectively. Now, keeping the temperature constant, if the pressure of a given mass of the gas is very low, the volume of the gas will be quite large according to Boyle's law. Then volume of the empty spaces will be large. The molecular volume can be neglected under these conditions. On the contrary, if the pressure of the gas will be very high, then the corresponding volume will be small. This means that the volume of empty spaces will be small and the molecular volume of gas cannot be neglected. Thus, the gas will show maximum deviation from the ideal gas behavior at high pressure and minimum deviation at low pressure. Second assumption is the forces of attraction and repulsion among the gas molecules are negligible. This is true when the gas molecules are far apart. This can happen only at high temperature since the average kinetic energy will be also quite high and gas molecules will be far separated from one another. However, if the temperature of the gas is very low, the average kinetic energy being small, the gas molecules will be quite close to one another. These forces cannot be neglected and the gas is expected to show maximum deviation from the ideal gas behavior at low temperature. To explain the behavior of real gases, in 1873, J.D. van der Waals modified the ideal gas equation by applying appropriate corrections so as to take into account the volume of the gas molecules and the forces of attraction between the gas molecules. Van der Waals equation has been obtained by modifying the ideal gas equation by applying corrections for the volume and pressure. Let us first apply correction due to molecular volume. The assumption of kinetic theory states that the actual volume of molecules is negligible and does not cause any error at low pressure. At high pressure, the molecules of gases come close to each other. The volume occupied by the molecules themselves becomes a considerable fraction of the total volume enclosing the gas. So, at high pressure, the actual free space available for the movement of the molecules inside the vessel is not the volume V of vessel but V minus NB. Here, B represents effective volume or co-volume of molecules and N is the number of moles of gas. So, corrected volume Vi is equal to available volume V minus non-compressible volume NB, that is Vi is equal to V minus N multiplied by B where small n denotes the number of moles of gas. Let us calculate co-volume B of a gas. Let us consider 1 mole of a gas has molecules equal to n, which is equal to 6.02 into 10 raised to the power 23 molecules. Let each molecule be a sphere with radius equal to r centimeters. So, volume of one molecule is equal to 4 upon 3 pi r cube. The closest approach of two molecules is equal to 2r. The excluded volume for two molecules is equal to 4 upon 3 pi 2r whole cube is equal to 8 into 4 upon 3 pi r cube. The excluded volume for one molecule is equal to 1 upon 2 into 8 into 4 upon 3 pi r cube. It is equal to 4 into 4 upon 3 pi r cube. The excluded volume for n molecules is equal to 4n into 4 upon 3 into pi r cube. It is equal to small b. Thus, excluded volume or co-volume or effective volume or non-compressible volume of a gas is 4 times of the actual volume n into 4 upon 3 pi r cube of molecules at rest. So, corrected volume is equal to V minus B for 1 mole of a gas and V minus NB for n moles of a gas. Next, we will discuss pressure correction due to intermolecular attraction. The assumption of kinetic theory states that molecules do not exert intermolecular attraction, do not cause any error at low pressure. At high pressure, the molecules come closer and intermolecular attractive forces become very high.
ਮੰਨ ਲਵੋ ਕਿ ਦੋ ਮੋਲੀਕਿਊਲਸ C ਅਤੇ W ਕ੍ਰਮਵਾਰ ਕੰਟੇਨਰ ਦੇ ਸੈਂਟਰ ਵਿੱਚ ਅਤੇ ਕੰਟੇਨਰ ਦੀ ਦੀਵਾਰ ਦੇ ਨੇੜੇ ਪਏ ਹੋਏ ਹਨ। The molecule C is equally attracted from all sides by the surrounding molecules. Thus, these attractive forces mutually cancel each other. So, the net resultant attractive pull on molecule C is 0. Molecule W container ਦੀ wall ਦੇ ਨੇੜੇ ਹੈ। This molecule is surrounded by other molecules which are not equally distributed in opposite directions. This molecule, which is just going to strike the wall, is being pulled inwards by the molecules lying behind it. So, this molecule will strike the wall of the container with less force. Since the pressure of the gas depends upon the force with which the molecules hit at the wall of the container per unit area per second, thus observed pressure P is less than ideal pressure.
The observed pressure P becomes less than ideal pressure by a factor P called as pressure correction term. So, ideal pressure is equal to observed pressure plus pressure correction term, or Pi is equal to capital P plus small p. Here Pi denotes to ideal pressure, capital P denotes to observed pressure and small p denotes to pressure correction term. Inward force P exerted on molecules just to strike the walls of the vessel is proportional to the number of gas molecules in the interior that are attracting it inward. These are also proportional to density of the gas D. This is equation number 1. The number of molecules that are striking at the walls of the vessel at any time are also proportional to the density of the gas D. This is equation number 2. On combining equations 1 and 2, we get the correction term P is proportional to density of the gas near the wall and the density of the gas inside. Hence, P is proportional to square root of density, or P is proportional to D square, or P is proportional to N upon V whole square. Here, N is the number of moles present in volume V. Or we can write as P is equal to AN square upon V square. Here A is the proportionality constant called coefficient of attraction. So, ideal pressure Pi is equal to capital P plus small p, which is equal to capital P plus A, N square upon V square. It is so because small p is equal to A, N square upon V square. Also, ideal volume Vi is equal to V minus Nb. It is the corrected volume of the gas. Putting the value of Pi and Vi in gas equation Pi-Vi is equal to nRT, we get P plus A N square upon V square into V minus Nb is equal to nRT. Or P plus A upon V square into V minus B is equal to RT for 1 mole of gas, where A and B are the van der Waals constants. This is called van der Waals equation. This equation explains the behavior of all real gases quite satisfactorily. Let us discuss about the units for van der Waals constants A and B. Unit of constant A. As P is equal to AN square upon V square, or A is equal to P into V square upon N square, or it is equal to pressure into volume square upon moles square. If pressure is expressed in atmospheres and volume is in liters, then the units of A should be atmosphere liter square mole square inverse. The constant A is related to the intermolecular attractive forces. Greater the value of A, greater is the strength of molecular interaction. Unit of constant B. B is the excluded or incompressible volume per mole of the gas. Hence, units of B must be the units of volume, that is liter per mole or liter mole inverse. At the end of the topic, let me ask you one question. And the question is, the compressibility factor Z for a gas is less than 1. What does it signify? And the answer is, this indicates that the gas can be compressed more as compared to an ideal gas. So students, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਟੌਪਿਕ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਇੱਕ ਹੋਰ ਨਵੇਂ ਵਿਸ਼ੇ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ। ਗੁੱਡ ਬਾਏ।